Oh, awesome. Okay, thank you. Hello, everyone. I'm Marzena Sniegowska. I am postdoc at Tel Aviv University in a group of Benny Trachtenbrot. I am mostly working on flaring AGNs in observations and in theory, which is quite nice because if someone asks you about theory, you say, "Oh, I'm doing observations." Quite comfy position too. Yeah, so we will talk about supermassive black hole related transients, and then also about some theory behind it, which will be, of course, biased because I will mostly show what I'm working on. So we've already heard a lot introduction, really nice one, about this supermassive black hole related transients. Firstly, let's take a look on transients which we see in already existing AGN. So we have changing look AGN with timescales of months and years, which is already very challenging from theoretical point of view if we use Shakura-Sunyaev disk. And here you can see really pretty light curve with the soft. It's slowly going, it's dimming. And here we have a spectra. So this is a spectrum before this dimming. So you can see here blue continuum, and here we have H beta, we have nice H alpha. And after 12 years, there is another spectrum, which is, quite flat. There is no more this blue continuum, and also we don't see those broad components in Balmer lines. We also have some peculiar events in AGN. So this is from Lydia Makliani work, and this is Bowen fluorescence flare in pre-existing AGN. This is a spectrum from Lamos taken before the flare. So you can see here we have a broad line for H beta, which means we have BLR there. And then we have boom, and then some another peculiar boom. That not only H beta became stronger, but also you have this funny feature called Bowen fluorescence, which we've heard also from Pietro. And also we have some other black hole related transits, not necessarily in AGN. We have tidal disruption events. And here I want to focus on spectra mostly in this one. So here you can see helium-2, which is very broad. And as very broad, I mean, it's like 10,000 kilometers per second. Whereas in this Bowen one, those lines are around 2,000. And also we have quasi-periodic eruptions. About this, I will just briefly mention, because on this you can give the full seminar, and I'm not going to. But they are very peculiar sources, because the masses of supermassive black hole are 10 to 5, 10 to 6, and the time scales of these events are hours or days. So good luck explaining that with Shakura-Sunyaev. I tried, so I know what. For now, we know like 10 of those sources, which is, yeah, really interesting. And about tidal disruption events, like, are they actually, yeah, we have also this repeated partial tidal disruption events. And here you can see one example with repetitive. So now we will talk about possible scenarios for those recurring events in AGN. And also yesterday Paula mentioned about it, so I will briefly mention that the obscuration seems to be the most challenging. Also in Grisha's this funny source which did dimming, it was also quite challenging to explain it with obscuration, because then where should be this obscurer? How big should it be to obscure the whole VLR? And how fast should it move? Also, there was really nice work by Hatzemaker. In terms of changing look, they checked spectropolarimetry, because in polarized light, you should see a scatterer, and this obscurer should scatter some light. And for this 10 changing look sample, they found that the scattering, the polarization is very low. So probably it's not due to obscuration. And then we have tidal disruption events, and I mean those classical tidal disruption events. Then the timescales are quite challenging, and also with spectra, in terms of changing look, like we don't see the helium, the broad one. And also, yeah, the timescales are mostly the problem in all of them, actually. And then we go to my favorite one, changes in accretion rate, whatever you mean. Yeah, MRI, radiation pressure, ionization. And yeah, let's go to this madness now. We will start, all of the models I'm showing were inspired by changing look, AGN. But if we see flare in AGN, actually, they could be used there also, yeah? Why not? So here it's a model proposed by Noda and Dan for one particular source, which is Markarian 1018. It was observed in X-rays, but also in optical. So let's start from here. Those are best fits from X-ray observation. It was done with XMM and also with Swift. And we can see here mostly the components. This is a soft axis, and also this is the hard X-ray part. And you can see that within time, the soft axis dropping. And here you can see archival spectrum from SDSS from 2000, which is like before those observations were done. And then follow-up spectroscopy with, and you can see like the Bowen. Okay, I'm thinking about both. The broad H beta and H alpha, yeah, changed dramatically. Also here, helium is not visible anymore. And they proposed explanation that we may have warm corona, which is responsible for a soft axis, which we see here. Then this warm corona evaporates into ADAF. ADAF is advection-dominated accretion flow, which is assumed to be geometrically thick, but optically thin medium. So this soft axis evaporated, and this lack of soft axis affects what we see in the optical. And it can also change vice versa. It can come back, yeah, like ADAF may condensate, and again, we may see the soft axis. And it works for this source, but there was another work for another changing look where there was no warm corona before the outburst in AGN, which doesn't mean that this model doesn't work, but it means that we probably have few mechanisms. And in different sources, different mechanism maybe dominates. Yeah, so now there will be another source and another proposition for this particular source. We will focus now on the spectroscopy. You can see here this really nice SDSS blue spectrum. We have here blue continuum. We have this blue H beta and H alpha line. There was then follow-up spectrum from both 10 years after. And you can see here that this blue continuum dropped, but the emission lines are still here. And then it was follow-up with Palomar after more or less 10 years. It came back to what we saw. And the proposition for this source was that we had geometry like this. We had some kind of puffed up disk. Then it happened some triggering event, maybe due to magnetic field, our favorite one, configuration, which caused this part to smear out. There was the cooling front, which also affected what we see in the blue continuum, because we are talking about inner part of accretion disks. And then it came back as a heating front to what we've seen after. So for those repetitive events, it would also work. Yeah. And here I will show you a really nice source, not only because Benny was working on it, but I like this source and those works from two reasons. One of them, because it shows that we should befriend another astronomers from different field a bit to better understand what's going on. Because Benny was leading this optical and UV part, whereas Claudio Ricci X-ray 1. And another part is that the more spectroscopy or the more data, the better, because then we can really understand and came up with different better models, yeah, to understand slowly what's going on. So we had flare in optical in UV, then corona, the X-rays reacted, Yeah, it dimmed. And more or less here we have the, when we started to see this UV flare, and here you can see that there is not much going on in HB, and it slowly showed up more or less here after 3 months, which is more or less when you read papers about reverberation mapping, this is more or less the time scale which we expect for a light travel time to go there. And then like, okay, it started here, and then of course it took some time to ionize fully the broadline region. So here it, and I think it's a bit different from how I was saying about the source, because the broadline region is getting created. Here, probably we already had the medium. It just needed to be ionized. So probably the timescales. I thought like maybe that's why the timescales are different. Yeah. And here the proposed model was about the establishment of magnetic flux, which means that this was based on a magnetically arrested disk, which means that we have a lot of magnetic flux accumulated in this inner part of accretion disk. And if we think about the sun, yeah, the sun sometimes changes polarity, yeah. So with this idea, we can also probably, if we have magnetic flux, maybe we can change the polarity of this magnetic flux. It will affect what's happening in the source. So this model was based on this idea that we have this reestablishment or change of polarity, which dimmed, first caused the UV flare, then the X-ray dimmed. And after this polarity change finished, it got rebuilt to what it was, at least in X-rays. Yeah, and you can see it in the data. There was also one idea what can be happening in changing look. It's close binary supermassive black holes. And in this paper, they showed how the luminosity would be affected depending on how the black holes are spinning and how they are rotating. And it will be really nice to see some simulations to check how the light curve looks like, for example, from this. Because, okay, it may sound a bit exotic, but also the sources we see are exotic. So like, why not to explore a bit, yeah. Yeah, now we go to my favorite part, which is instability of radiation pressure dominated Keplerian disk. I decided to not put too many equations. We will just, but if you want, I have backup slides. But let's stay here for now, okay? So assuming Shakura-Synaev disk model and taking into account the equation of surface density of accretion disk and the temperature of accretion disk, and solving it to get stationary solution, we are getting something which is called stability curve, an S curve. Yeah, so we have this line of solution, and this instabilities here were found not in Shakura-Synaev, but it was not much after. Yeah, Shakura-Synaev was from 73, so like exactly the same year. There were a few works after 73 saying that there will be one part of solutions which is not exactly stable. And we have this S-curve with our unstable solutions here. And this is just for stationary. So if you want to do this time-dependent solving of accretion disk, that's where you can start. From here, you get your initial condition, how to kick the accretion disk to start to do this limit cycle like an engine. And we have here 3 phases in of the outburst, because this luminosity does not depend purely on the temperature, but also on what's going on with this surface density. Yeah. So we have this viscous phase, which is a bit slower. Here I'm showing it just for X-ray binary because it was faster to calculate. But you know the method will work for higher masses. So we have this viscous part, then we have the heating part, which is here, and then the medium is cooling down. So from here we start to put mass into accretion disk till it's getting unstable, yeah. And then it starts. It's like, I don't know, a Carnot cycle, kinda. And why we even bother about this radiation pressure instabilities? Because if you wanna do some fast check for accretion disk, you can also use X-ray binaries. And there is at least one X-ray binary with found really nice called heartbeat variability. And it was modeled using this radiation pressure instabilities. And it seems it's working, yeah, like the shape, quite nice. There was work by Professor Janiuk from CFT. So we got inspiration from that to use it for bigger black hole masses. So with Professor Czerny from Warsaw, we came up with the idea that to use it for higher black hole masses, the same mechanism. And we have this sketch, and we will focus on this, but let's slowly go through it. So we have black hole mass, which we are just assuming in the equations. And we are focusing only on this unstable part of the disk. And ADAF and this stable disk are just treated as boundary condition. Yeah, we are just focusing on this part. And we are following the time-dependent evolution of this zone. And we are scaling our time scales with where we locate this unstable part, and also how broad or narrow it is. Here I will show you. First, we will focus on this right side, and then we will come to the data. So you can see that if we just calculate m dot, which scales in with the luminosity, but we wanted just to focus on the time scale to see if we are able to get time scales of years using this model. That was our goal. And we changed few parameters in the model just to explore what's going on. So we changed m dot, we changed alpha, and also how broad is our unstable zone. Yeah, and you can see that with this unstable zone, we are able to get timescales of 10 years, which is quite what we wanted from the data. And here are two examples of sources which are known that they had some repetitive events, and they are changing look. And then we thought, would it work for QPEs? Because you see that this work is from 2020, so we were working on it in 2019 when the first QPE source showed up by Giovanni Minuti. He was really kind to provide us the data. So we wanted to check if with this model we can get those hours for 10 to 6 solar masses. And we came up with another model because for this it was very tricky. So we improved this unstable zone. We added also corona above, and as corona I mean hot one, not warm corona. And in an unstable zone, we are not computing it just like one thing, but we have a grid of points we calculate. And if you cut the radius of this unstable zone, just by cutting the radius, don't think about any magnetic field, nothing. We are just cutting the radius. We are getting already timescales of 80 years, which is okay, still a bit too much, but we came from thousands. We don't do it because then it will just flow slowly. But if we just cut it, then already we are in 80 years more or less. But we decided to check what will happen if we add magnetic field to shrink the timescale. So we borrowed idea of so-called dead zone for this model, because also in this model we allowed for mass exchange between the accretion disk and corona. And with this one, we did not. So it was, more efficiently going towards the black hole. And here we have a period. This is for 10 to 7 solar masses, so more or less for changing look. And I expected that with increasing, this is a coefficient how strong the magnetic field we were adding in comparison to other parameters. And I hope it will drop. Like we will start, I don't know, maybe from 50 years, and we will, with increasing magnetic field, we will just, you know, and slowly increase the time scales till the disk stabilizes. And what was happening? Yeah, it started to increase. And it was the last year of my PhD, so I felt like, oh my, like what to do now? But okay, I was like, okay, thank you. Yes, I was calmly calculating it, and here we went to drop it. I was like, okay, there is a chance, but the light curve looks different, so I would call it was like a different mode of pulsations. And then I started like, okay, we need to drop it more, and then it came to 200 years. So I was already in the accretion disk was in a different mode. I was in a panic mode. We went here. It's like, okay, there is some narrow range of parameters where we can get few years. So like, okay, but it's very narrow range. So what about different ideas? Yeah. So we decided, and here I wanted to show you why we thought that it will drop nicely, because for X-ray binaries, that's what happened. Then we checked 10 to 5 to see if we could use it for QPEs. We got this, so I also expected like, okay, for 10 to 7, it will also work this way. But it was, yeah, quite dramatic here. And yeah, increasing the black hole mass was making the periods longer, but the scale of magnetic field strength was the same for all of the black hole masses. And we decided to just cut the radius. Here it was just to check what's going on. We didn't go here because, yeah, around 10 or something, it's a bit dangerous to go without GR. So we checked mostly those two, 50 and 30 Schwarzschild radii. And what you can see, especially here, we have some recurring flares on a year timescale with a very rich structure. And because it's like 50, we are in the really inner part of accretion disk, which is responsible for the UV emission. And now, really fastly, I will go through Bowen fluorescence, which was expected from the simulations, from computations to be seen already. It was, yeah, in the 80s. And it was explained by Pietro, so maybe I will skip it. And I will go to what we saw. We expected that those lines should be comparable with H beta, and they are in some cases, where we see the flare, and then here it's a really nice source, which was the first one found by Benny. And here we have this LOI source found by Lydia Makliani, which we have proof with the spectrum that it was an AGN. And here I will show you my nightmare source, which we have one spectrum from SDSS, which was taken somewhere here, yeah, before the flare. Now we see in optical, we see flare, and somewhere here there was another spectrum, and we see the same. Like when I was fitting it, I thought like maybe I made a mistake and I took this spectrum twice, but no, it's the same. This is from Keck, this is from SDSS. Then we have, boom, another flare with some funny structure. Also here there is structure. And there we go, Bowen. In infrared, it looks like that. It's really nicely following what's going on. And also what is funny that between those peaks, optical and infrared, and also here, it's the same size. It's the same time scale. Quite nice. And now we go to X-rays from Swift. And you can see that we have this structure in UV, and also something in X-rays is happening. And if we compare this source, the spectrum of this source, which is this, to Bowen, you can see that it's similar. And if we compare it to the TDE, it's less similar. So we have really nice flare, double flare in AGN with very peculiar X-ray behavior, and it's different from normal TDE, similar to other Bowen fluorescence lines. Yeah, and that was my nightmare source. And when I think about it right now, it's like when you go to some touristic places and you see those guys who have a lot of instruments, yeah, like a plate and this this huge drum. So this is more or less what this source is doing. Like you don't expect, and there's like X-ray, like everything at once. Yeah.
Thanks for the very interesting talk. I didn't quite get what's the point of this ADAF component and what's the boundary to it?
Boundary. After that, we assume it's electron conduction. It just evaporates.
You need the ADAF.
Why do we need it? Because it cannot go directly to black hole. We need something to get rid of the rest of the energy.
Thank you so much. Super cool. If we go back to one of the spectra that you were showing now of ULC, okay. So I think in one spectrum before you were actually putting the gamma and H delta at the same redshift as the 17 BGD. Like what I notice is that from this spectrum, it looks like your H beta is at a different, O3 are different redshifts compared to your H gamma delta Bowen lines. And I'm curious what you think about it, because in my source, I also have the Palmer component shifted with respect to
Really? Because I thought it's maybe due to quality of spec. Not.
No.
Okay, so okay.
Like before.
The source was supposed to be a repeating TD, right?
Yes.
So in your interpretation, this is not a TD, it's like a Bowen fluorescent.
Okay, how to answer to it politically correct? You can see that we have a rich structure after the flare, and what I was able to model, it also had some rich structure. In accretion from I think it can be from accretion disk stabilities. Okay, I will just put it this way. I think, but the model is not yet good enough to give you the spec. But I have this, maybe because I am biased, because I like the model and I work on it so much. But I think it's tempting to use something, because we have really strong UV. So I guess it should somehow affect. Yeah.
I just want to make a quick comment. Maybe we will hear about that on Monday from the dynamicists, but repeated partial disruption events are expected. In fact, are expected to be probably as numerous, if not more numerous, than full TDs. It depends, of course, on the regime into which stars are scattered into the lost cone, whether they diffuse from outwards or they just scatter inwards. But it's, from what I understand, it's much well expected that must be a regime in which stars slowly diffuse in, and at some point they reach the regime in which the outer layer of the star start being disrupted, and this may happen multiple times. So there is nothing exotic or particularly strange. I don't think we know exactly what is the relative rate, but as we think we find TD, I think we should be open to the idea that we should be seeing repeated TD. This is nothing strange, I think.
Yeah, but what is strange?
I'm not saying particularly about this.
Yeah,
this
but
was a generic.
yeah, that is true. But what is puzzling me here about this source is like the light curve, the dimming, is taking much longer than what is seen in partial TDE.
Mhm.
So that's something I don't understand, to be honest, why we.
Maybe just Paula. Sorry, but nothing in. Can you show the data, please?
Yes.
Nothing in this source looks like a TD, apart from the fact that it, went up and it goes down.
Yeah,
It goes down very slowly, repeats. The second flare is higher than the first flare. No broad helium, no crazy soft X-rays, if I remember correctly. I mean, softer than usual, but typical for stable AGN.
I agree. Actually, this source was included in my sample of anomaly detection. Maybe you can mention this. So it was a candidate there for a changing look AGN. In my paper where we use learning to identify changing look AGN candidates. So yeah, I agree. This case, and yeah, nothing there besides this transient-like shape tells you that.
Okay, let's again.
Yes.
This afternoon.
Yes, couple of announcements. Well, first of all, please send your slides to workshop at MeUp so that we can play some for everybody that is here now or will be here next week. Or if you want, you can also send it to me. I can do the same. So that's quite important. Also, people have been asking me, these talks are all recorded. And you know, I sent around a consent form for this to be uploaded on YouTube. I know that Sandra and the other from the program office are working on the videos. They need to do some editing and trimming. So that's why the YouTube channel is still not populated with them, but they told me they're working on that. Most of you have already sent the consent form. So eventually they will slowly start appearing. So also don't forget to just click on the consent form, unless of course you don't want your video to appear on YouTube. If you have some specific requests about some slide that you prefer not to be shown, you should let me or Sandra know. We'll see what we can do with that. I am not 100% sure. And these are the practical things. Of course, today's the end of the second week. Some of you will leave. So I would just want to thank those that have been here very much. It's been a pleasure to have you around. And I hope you have enjoyed being at MeUp. If you have been inspired by the discussion and the talks, if some new project come out of this workshop, the MeUp organizer would be very happy if you can acknowledge this into your publication. You go on the MeUp website, there is a for visitor part, and there is a couple of lines of text. And we will appreciate if this is something that you that have inspired you. Among the people that will not come back after this weekend is one of the coordinators, Ben, who put a lot of effort into preparing, organizing, thinking about it, and also specifically during the time here in making sure that the afternoons are active. And, you know, I really want to thank particularly Ben for all the work that he's done. It's been a great pleasure. Actually, I guess very soon, and immediately you see without Ben for a reason having to do with the very good weather and the time constraint for the other coordinators. This afternoon, we don't have anything planned. You can go out and enjoy the sun, and for those of you still around, we'll see you again.
So there is no discussion session?
No.
Oh, okay.
Yeah. It's a good thing I'm leaving. Otherwise, I would feel
Thank you. I'm start really appreciating who put all the hard work on that. But we will come back on Monday with more topics and more discussions. That was for see you next week for those of you. Thank you.
Yes, okay. Yeah, like next week. I'm leaving on Sunday, yeah.
Keep in touch. Last week.
Yeah.
I guess that's fine.